Okay, hi everyone. Let's get started again. Okay, so first of all, let me just say a bit about assignment 5. So assignment 5 is coming out today. It's a brand new assignment, so you guys are the guinea pigs for that. And so what it's going to be, it essentially builds on assignment 4, though it's okay if you didn't do perfectly in assignment 4, though I think actually most people did. And what we're going to be doing is adding convolutional neural networks and subword modeling to the neural machine translation system, seeking it to make it better. So this assignment is coding heavy, written questions light. So, I mean, the coding that you have to do sort of isn't actually really more difficult than assignment 4. It's kind of like assignment 4, but what we're hoping is that this time you will be able to do it on your own. What I mean by that is for assignment 4, well, there was tons of scaffolding telling you what everything should be, and there were all of these auto-grader checks, and you could keep on working on your code until they passed all the auto-grader checks, and everybody did. And so it was very kind of coddled, shall we say. But I mean, I guess what we're really wanting to achieve is to have a more, question. Yeah, so what we're hoping is that this can be useful. It'll be short-term pain, but useful as being a more effective ramp to doing the final project and indeed for the rest of your life, right? And the reality is that in the rest of your life, you sort of, if you're going to be doing things with deep learning, you kind of have to work out what kind of model to build and which pieces to stitch together and how to write some tests to see if it's doing something sensible, and if it's not doing something sensible, to figure out how you could change things and try different things and get it to work sensibly. And so that's what we're hoping that people can do in assignment 5. So you've got to figure things out, should write your own testing code. We don't have a public auto-grader, so that's part of working out your own sanity checks, trying to do things like what I talked about last week of sort of getting simple bits working, confirming that they work on minute amounts of test data and so on, and doing things more sensibly. I mean, in particular, the one particular part of that we were planning to do for this assignment, I was looking for it, but it's on the next slide. So for this assignment and beyond, we're going to enforce rules more like they are in CS107 for those of you who are undergrads, meaning that the TAs don't look at and debug your code for you. And so, you know, of course, we still want TAs to be helpful. Come to them with your problems. Talk about how you're meant to use different things in the PyTorch library, but you shouldn't be regarding it as the TA's job of, here's a big Python file, can you tell me what's wrong with it and fix it up for you? Okay, the precise policy for that's written up on Piazza. Okay, so any questions about that, or do I go straight on in? Okay. Yeah, so today's lecture, in some sense, today's lecture is an easy lecture. So last time's lecture, there was really sort of a ton of new stuff of other stuff in neural networks that you hadn't seen before. And we did convnets, and we did pooling layers, and we did highway and residual connections, and batch norms, and I don't know, whatever else we did. Size 1 convolutions, I guess. So there are tons of new stuff. Really in this lecture, in terms of sort of neural network machinery, there isn't any new stuff at all. So this is really easy. And this is also really a new lecture, but it was sort of put in for a reason. And the reason for this relates to a kind of remark I made last time about how lots of stuff keeps changing in neural network land. So at the time we first designed this class, and the way a lot of the structure of it still is, that sort of around 2014-15 when we designed this class, it was basically axiomatic that all deep learning models for natural language processing worked off words, and therefore it completely made sense that we start with word vectors and then we start looking at things like recurrent models over words. Whereas the fact of the matter is, in the last approximately 3 years, there's been a ton of new work, including some of the most influential new work, that's building language models that aren't being built over words, that they're being built over pieces of words or characters. And so this lecture is sort of meant to give you some sense of these other ways of doing things and some orientation to some of the things that's going on, but the actual kind of models that we're looking at are sort of using all of the building blocks that we've already looked at, things like RNNs and ConvNets and things like that. So let's get into this. So I'm going to start off with a teeny bit of linguistics, of learning about the structure of language for sort of lower level units of language, and then we'll see how that pans out for things like character level models. So in linguistics, if you start at the bottom of the totem pole, the first level of linguistics is phonetics, which is sort of understanding the sounds and the physiology of human speech. So that's sort of like physics or physiology or something, right? There are mouth parts that move, there are ear parts that act as filters, and there's audio waves in between the two of them. So that's kind of uncontroversial in some sense. But above that level, the standard thing that people do for the analysis of human languages is to say, well, human languages seem to make use of a relatively small set of distinctive units, which are then commonly called phonemes, which are actually categorical. And the idea here is that, well, our mouths are continuous spaces, right? That they've got these various bits of their mouths, like, you know, tongues and pharynxes and so on, but it's a continuous space. So actually, we can make an infinite variety of sounds, right? So if I open my mouth and apply voicing and just waggle my tongue around, I can go, and I can make an infinite variety of different sounds. But the reality is that human languages aren't like that, that out of that infinite variety of sounds, we distinguish a small space of sounds. And something that happens when languages change is that the space of sounds that are seen as important and distinguished in a language change. And that happens even within inside one language as is English, and I'm about to give an example of that. So people in cog psych talk about the phenomenon of categorical perception, and what that means is that really there's something continuous, but that humans perceive it as belonging to fairly sharp categories. And, you know, you can use that for sort of, you know, styles of clothing or whether someone counts as fat or not. But the most famous examples of categorical perception are in language, where we can make an infinite variety of sounds, but people perceive them as categories. And so effectively what that means is when you have categorical perception, the differences within a category are sort of perceived to have shrunk. You barely notice them at all, where differences across categories are expanded and very clear. And so one of the cases that's sort of studied a lot is what's referred to as sort of voice onset time. So lots of languages, including English, have pairs of sounds like P and B, pa and ba, and they differ based on when voicing starts. So B has a voice sound like a vowel with an R in it. And, well, that's a continuous parameter. You can sort of make any point along a spectrum between a P and a B, but human beings who speak English perceive just 2 points on that spectrum, and you don't sort of really notice the fine differences between them. Some languages distinguish more points on the spectrum. So Thai distinguishes 3 different consonant sounds depending on the voice onset time. Something that might be more accessible to you is, this is an example of language change. So for a speaker like me, there is court and cot, and those are different vowels, and I hear them as different vowels. But if you are someone who grew up in the southwest of the United States, then these are exactly the same vowel and you don't distinguish them. That you thought I said the same thing twice, even though I was saying 2 different vowels. And so that's where, even at a dialectal level, that people develop categorical perception as to which distinctions and sounds they're sensitive to or not sensitive to. Okay, and I mean, why I'm mentioning this is in some senses these sound distinctions, of categorical sound distinctions, that are what a lot of our language writing systems that we'll come to in a minute record. Okay, so in traditional linguistics, you have sounds, but sounds don't have any meanings in language. So p and b don't have meanings, and r and e don't have meanings. And so people then normally distinguish as the next level up. Morphology is parts of words, and this is seen as the minimal level that has meaning. And so the idea is lots of words are complex and can be made up of pieces, but these pieces do have meaning. So fortune has a meaning. Fortunate, you end in this 8 ending, which sort of gives fortune to somebody. So that means, having fortune, that has a meaning. Has a meaning, which means to reverse that. So unfortunate means that you don't have fortune. And Lee then has a meaning of turning this all into an adverb. And you can say, unfortunately, not having gotten fortune, something happened. And so these sort of pieces of words are then the minimal things that have meaning. Almost no work in deep learning has tried to make use of this sort of morpheme level of structure. Actually, me and a couple of students 6 years ago did actually try and build a system where it built these tree-structured neural networks that put together meanings of words out of their pieces. But that really isn't an idea that's taken on widely. There's sort of a reason why it hasn't taken on widely, which is doing this and working out the semantically meaningful pieces of words is kind of hard. And a lot of the time in NLP, what people have found is you can just about get the same kind of results if you just work with character n-grams, the kind of units that you put into the convolutional neural nets. Because if you just have a model that uses character trigrams and you have sort of start of word un and NFO and so on, for going through to LY, end of word, that those different units, there's different character trigrams in a distributed way will pick up all the important meaning components of the word pretty well, and that's just good enough. And that's actually a very classic idea that's sort of been revived. So back in the second coming of neural networks in the mid-80s into the early 90s, there was quite a bit of sort of controversial work on the structure of language, and in particular Dave Rumelhart and Jay McClellan. So Jay McClellan's still in the psych department here, if you want to look him up in your spare time. They proposed a model of how to model generating past tense forms in English. So this was sort of a cog-sci experiment of, can we build a system that can learn past tenses of English verbs? And the difficult part there is many verbs are regular, you add the kind of ed ending, but some words are irregular, and you had to sort of learn about the irregular patterning. But the way they did that, I mean, partly because this was sort of early days with respect to sequence models, is that they used a representation where they represented words precisely with these sort of character trigrams, and that was the representation of words that they used and fed forward in their model. And that, idea was met with a lot of controversy by linguists, philosophers, and other people with their ideas of language, and so there was a lot of debate in those days about that. But as a purely engineering solution, that sort of proved to be a pretty good way to do things. And so this decade, there's been other work, which includes the model developed in Microsoft of a sort of a deep semantics model, where what they're using is these kind of character engrams to put meaning over words. Okay, so now we might be interested in building models that aren't over words. So we're going to have a word written as characters, and we're going to do something with it, such as build character engrams. And so something that is just useful to know is, there's actually a fair amount of variation between languages when you do this, so it's not all the same stuff, right? So the first problem is there are some languages that don't put spaces between words. The most famous example is Chinese. But an interesting fact for those people of European ancestry is that, when the ancient Greeks wrote ancient Greek, they didn't put spaces between words either. It was actually a later invention of medieval scholars who were recopying their manuscripts, who they decided, maybe that'd be easier to read if we put spaces in, and that they started doing it. Most languages these days do put spaces in between words, but even then there are sort of a lot of fine cases. So in particular, a lot of languages have some sort of little bits of stuff which might be pronouns or prepositions or various kind of joining words like and so, and which sometimes they write together and sometimes separately. So in French, you get these kind of pronominal markers for you, you have brought. And these kind of little words in pronunciation just sort of run together as je vous ai, and arguably it's almost one word, but it's written as separate words, where there are other languages which sort of stick things together, where arguably they're separate words. So in Arabic, you get pronominal clitics and some of these sort of joining words like so and that they're sort of written together as one word, where arguably that they should really be four words. Another famous case of that is with compound nouns. So in English, we write compound nouns with spaces between them so you can see each noun, even though in many respects compound nouns, something like whiteboard, behaves like it's one word, or high school, whereas other languages, German is the most famous case, but also other Germanic languages, just write them all as one word, and you get very long words like that. So we're going to get different words if we just use spaces and don't do much else. Good. Okay, yeah, so for dealing with words, there are these practical problems, and we sort of already started to touch on them, that if you try and build word-based models, there's this huge space of words. And well, strictly there's an infinite space of words, because once you allow in things like numbers, let alone FedEx routing numbers, or if you allow in just morphology, when you can make those ones like unfortunately, you can just expand the space of words, so you get this large open vocabulary. English, a bit problematic. It gets way more problematic in a lot of other languages. So here's a lovely Czech word, to the worst farmable one, where you can make sort of much more complex words, and lots of other languages, many Native American languages, other European languages like Finnish have these sort of very complex words. Turkish has very complex words. So that's bad news. There are other reasons we'd like to be able to look at words below the word level to know things about them. So when you're translating, there's a wide space of things, especially names, where translation is essentially transliteration, that you're going to rewrite the sound of somebody's name as roughly, perhaps not perfectly correctly, but roughly correctly according to the sound systems of the different language. And well, if we want to do that, we essentially want to operate at the letter level, not the word level. But another huge modern reason why we'd like to start modeling below the word level is we live in this age of social media, and if you're in the social media land, there's a lot of stuff that's written not using the canonical words that you find in the dictionary, and somehow we'd want to start to model that. So in some sense, this is the easy case. Good vibes. But nevertheless, this is spelt with 1, 2, 3, 4, 5, 6, 7 O's and 1, 2, 3, 4. Oh, and also 7 S's. They match. I don't know if that's deliberate or not. Okay, so this style of writing is very common. And well, we're kind of sunk if we're treating things at the word level and we're trying to model this, right? That's clearly not what human beings are doing. We're sort of looking at the characters and recognizing what goes on. In some sense, that's kind of the easy case that you could imagine pre-processing out. There's a lot of harder stuff that then turns up. I guess there's sort of the abbreviation speak of I don't care, but then you sort of get a lot of creative spellings that come off of kind of reduced pronunciations like I'm a go, summon, and it seems like somehow we need something other than canonical words if we're going to start to deal better with a lot of this text. Oops. Okay, so that suggests we sort of want to start doing that with our models. And so that's led to a lot of interest in using character level models. And I mean, there are sort of 2 extents to which you can do this, and we'll look at them both a bit. One level is to say, look, we're still going to have words in our system. Basically, we're going to build a system that works over words, but we want to be able to create word representations for any character sequence, and we'd like to do it in a way that takes advantage of being able to recognize parts of the character sequence that look familiar so that we can probably guess what vibes means. And so that sort of then solves the problems with unknown words, and we get similar words, similar embeddings for words with similar spellings, etc. But the other alternative is to say, oh no, just forget about these words altogether. Who needs them? Why don't we just do all of our language processing on sequence of characters? It'll work out fine. Both of these methods have been proven to work very successfully. And I just wanted to dwell on that for one moment, and that sort of goes back to my morphology slide here. When people first started proposing that they were going to build deep learning models over characters, I mean, my first feeling was, oh, that is never going to work, because it sort of seemed like, okay, words have a meaning. It makes sense that you can do something like build a word-to-vec model, and that's going to really be able to sort of see words and their distribution and learn the meanings of the words, because words have a meaning. The idea that you're going to be able to say, well, I'm going to come up with a vector representation of H and a different vector representation of A and a different vector representation of T, and somehow that'll be useful for representing what a hat means once I put it through enough neural network layers, frankly sounded pretty unconvincing to me. But I guess, but it totally works, so I'm convinced now, empirical proof. And I think what we sort of essentially need to realize is that yes, at some level we just have these characters that don't mean much, but we then have these very powerful combinatory models with a lot of parameters in them, things like recurrent neural networks and convolutional neural networks, and that they're effectively able to sort of store and build representations of meaning for multi-letter groups in such a way that they can model the meanings of morphemes and larger units and therefore put together word meanings. So on one more detail on using characters from writing systems. So if you're a linguist, you tend to think of sounds as primary. Those were the phonemes that I mentioned beforehand. Essentially, deep learning hasn't tried to use phonemes at all. Traditional speech recognizers often did use phonemes, but in the deep learning land, you want to have a lot of data, and the way you get a lot of data is you just use written stuff because, it's the easily found data where you can get millions and billions of words of stuff. So that sort of makes sense from a data point of view. But the thing that ends up as a little weird about that is that when you're then building a character level model, what your character level model is actually varies depending on the writing system of the language. And so you kind of have these quite different writing systems. So you have some writing systems which are just completely phonemic, that there are letters that have a particular sound and you say that sound. Something like Spanish is pretty much phonemic. Sometimes it's a teeny bit complicated, so you might have a digraph. So this digraph, ngabulu, is kind of like the NG of English that is used for sound, like at the end of sing. But, basically this is just G, ya, woo. Each letter's a sound. You can read it, and it's just phonemic. That then contrasts from something like English, where all the non-native speakers know the spelling is terrible. It's got this sort of highly fossilized, once upon a time phonemic system in the 10th century or something. But now we have this system that words have fairly arbitrary spelling that doesn't actually represent the sounds very clearly. But it's sort of a phonemic system. But then there are languages that use larger units. This is Canadian Inuktitut, which I just put in there because it's such a pretty writing system. But there are a lot of languages that represent syllables by their characters. So you have something like this in Korean, for example, with Korean Hangul, that each letter is then being a syllable of a sort of consonant-vowel combination like ba. You can then go up a level from that, and if we get back to Chinese again, well, this is sort of also a syllabic system, you could say, but really the Chinese characters are much more than just the sound. They also have a meaning, that this is really then an ideographic system where there are characters with particular meanings attached to them. So they're sort of whole morphemes written as one letter. And, another example of such a language was Egyptian hieroglyphs, if you've seen those, that they're sort of ideographic systems where you have letters with meanings. And then you have language systems that sort of mix several of those. So Japanese is sort of a mixture of partly Moraic, partly ideographic system mixed together. So if you just sort of start off and say, okay, I'm going to build a character-based system, that's fine. But effectively, your character units like letter trigrams are just very different in a language like Chinese, where commonly a letter trigram will be sort of a word and a half, 3 morphemes with meaning, whereas if you're in something like English, your character trigram will be something like THO, which is still sort of much too small a unit to have any meaning. So moving right ahead. So there are these two kind of approaches. One was just do a completely character level model, and then the other one was sort of make use of characters to build bigger things that you're then going to put something like into a more word level model. So I'll do this one first and the other one. So for purely character level models, I actually showed an example of that last time. Do you remember? So there was that very deep convolutional network from the Kano et al. Work for text classification at the end. And that just started with a big line of characters and built these convolutional layers on top of it in the vision-like network and classified the documents. So that was sort of a completely character level model. But here's a bit more work on this. So people for machine translation have built machine translation systems that just read characters and write characters. And when people first tried to do that, it sort of didn't work, right? The people thought it might help to build character level models, especially for languages like Chinese, but people just weren't able to build models that worked as well as word-based models in either the pre-neural, the non-neural, or the neural world. But gradually that started to change. So people started to have successful character level decoders. And then sort of around 2015, 16, people started to show, look, you can actually do machine translation very well at just a character level with a few asterisks. And so here's a bit of work that we did, the Long and Manning one from 2015 on the last slide. So this is looking at English to Czech translation, and Czech's a good language to use if you want to motivate doing things at the character level, because it had those big horrible words with lots of morphology, like the example I showed you before, and I'll show you some more later. So people had built word level models for Czech, and they didn't work great, partly because of some of these vocab problems. So the sort of word level state of the art was, at this time, was 15.7 blue, which, as you know, is much less than we will accept for full grades in your homework. But, what counts as a good blue score depends on how difficult the language pair is. And so you're not doing Czech. So this was sort of the kind of neural MT model that we've talked about. So it was a seek-to-seek model with attention, and then it had extra stuff for substituting uncs with either a single word translation or by copying stuff from the source. So it was sort of basically state-of-the-art neural MT of 2015, got 15.7 blue. And the difference isn't big, but we were able to show, look, we could build this completely character level model, and it actually did fractionally better. So this sort of showed that in terms of translation quality, purely character-based models were completely viable at capturing the meaning of text as well as word-based models. Was this a great result? In some ways, yes. In another way, no. I mean, this model was truly terrible to train, right? So it took about 3 weeks for us to train this model, and at runtime it also worked very slowly. And so the problem with character level models, if you're putting them into something like an LSTM, is your sequences get way longer, right? So you've got about 7 times as long sequences as you used to have. And since there's not much information in the characters, you have to do back propagation through time much further back. And so we were running back propagation through time for 600 steps before we were truncating it. And so this sort of maybe that was excessive, but it made the models very slow. But we were able to show that it was able to get some of these good effects, right? So here's a Czech translating to Czech. Her 11-year-old daughter, Shani Bart, said it felt a little bit weird. And I don't know. Probably, does anyone speak Czech? Any Czech speakers? No Czech speakers? Okay, I don't speak Czech either, but we can see that this does interesting things. So the second line is the human translation into Czech, which we can use for some guidance. And so in particular, in Czech, there's a word for 11 years old, which you can see as that blue word on the second line. And you can see that despite 11-year-old was, that for 11-year-old, it's just able to perfectly produce letter by letter the Czech word for 11 years old, and that works beautifully. In contrast, for the word level model, 11-year-old was an unknown word because that wasn't in the vocabulary, and so then it had 2 mechanisms to try and deal with unknown words. It could either do a unigram translation of them, or it could just copy them, and for whatever reason it decided here that the best strategy was to copy, and so that was a complete fail. And if we go along for the character level model, another thing that it gets right that's really cool is the name Shani Bhatt. It's able to do this transliteration task that I mentioned just perfectly, and it turns that into Shani Bhattova, which is exactly what the human translator did as well. And so, it's actually doing some really kind of nice human translator like things. I mean, in fact, as best I can tell from spending a bit of time on Google Translate, it actually does a pretty good job in this sentence period. Right? This part here starts to be different from the human translator, but it's not actually bad. It's sort of a more literal translation. So this Chiti actually translates feel like in the English text, whereas the human sort of didn't actually use the word feel in the Czech version, that they just went was a little bit weird or strange. So that's cool. Okay. So here are a couple more results from this. So here's another system that was built the next year by these people, Jason Lee, Kyung-Hoon Cho, and Thomas Hoffman. So they wanted to do something that was, I don't know, much more complex and neural and understanding the meaning of the text on the source side. And so they were more using the kind of technologies we saw last time. So on the encoder side, you started off with a letter sequence of character embeddings, and then you're sort of using convolutions of 4, 3, and 5 characters to get representations up here. You're then doing a max pooling with a stride of 5, so you're getting a max pooled representation of pieces of the text for each of the 3, 4, and 5 convolutions. You're then feeding that through multiple layers of highway network and feeding that through a bidirectional gated recurrent unit, and that's giving you your source representation. On the decoder side, it was sort of the same as our decoder. It was just running a character level sequence model. So overall, so they were doing this, they were doing the opposite task. This is Czech 2 English. So they're starting to get better scores. But I mean, actually, if you're sort of looking at these different numbers, where I'll explain this system more in a minute, I mean, it sort of seems like the place where they get a lot of value is that using the character level decoder gives them a lot of value, where this very complex model on the source side is giving them almost no value at all. One more, even more recent paper. So this is Colin Cherry and fellow researchers at Google. So they last year did one more exploration of doing LSTM sequence-to-sequence style models, of comparing word and character-based models. And this is English to French, and this is Czech to English, which is what we were doing. And so in both cases, when you have a big model, the character model wins for them. The blue model comes out on top. But the sort of interesting thing is you sort of see these different effects depending on the morphological complexity of the language. So that for a language like Czech, it's a really good idea if you're wanting to build a good model to use character level, that they're getting about a blue point of difference there. Whereas for a model that's outputting French or English, there's actually a tiny but very little gain from using a character level model. Okay, so let me just explain these models. So these models are models of different sizes. So these models are using bidirectional LSTM encoders and one-directional LSTM decoders. So the simplest model just has a shallow bidirectional LSTM encoder and a 2-layer LSTM decoder. The middle model has a 3-deep stack of bidirectional LSTM encoders and a 4-deep stack of LSTM decoders. And the most complex model has a 6-deep stack of bidirectional LSTM encoders and an 8-deep stack of LSTM decoders. This is where it helps to work at Google. Probably for your projects, you don't want to go beyond 3 or 4. Stay over here. Okay, yeah, so these are the results. So basically what you're finding is if you're making sort of smaller models, you're better off with words. But as you go to big models, especially if you're in a morphologically rich language, you clearly start to win from the characters. But there is still a loss, which is essentially exactly the same loss that we were suffering from 2015. Right? This is the time graph. And so these are the same 3 models as over here. It's just the axis has changed to sort of sum the total number of LSTM layers. And so that, essentially, if you're at the word level, you can run any of these 3 models and they are fast, that you can be translating in sort of not much time. But for the character level models, your slope is much higher, so it starts to get quite expensive to run the deep character level models. Okay, so that's that section. So then chugging along, I then wanted to look at other ways of doing things. And so these are models that in some sense still do have words, but where we're going to want to sort of build word representations out of pieces. And there are essentially 2 families of ways that people have explored doing this. One way of doing it is to say, look, we just want to use exactly the same architecture as we use for a word model, except when our words aren't really going to be words. At least sometimes they're going to be pieces of words. And so those are often called word piece models. And in particular, there's one commonest way of doing it that's called BPE, which I'll go through in some detail. The other alternative is to say, well, we're going to kind of make a mixture or a hybrid. So our main model is going to work in terms of words, but we're going to have some kind of facility where we can construct a representation for otherwise unknown words by doing things at a character or lower level. And I'll show you a bit of that as well. Okay, so this is BPE. BPE is actually a pretty simple idea which has nothing to do with deep learning, but the use of BPE has sort of become pretty standard and successful for representing pieces of words to allow you to have an infinite vocabulary an infinite effective vocabulary while actually working with a finite vocabulary. So the origins of byte pair encoding and the name byte pair is nothing to do with natural language processing or neural nets. We're just writing a compression algorithm. So this is something like, compressing your documents with gzip. So what basic byte pair encoding is that you've got a collection of stuff with bytes, and you're looking for the most frequent sequence of 2 bytes, and you say, okay, I'm going to add that sequence of 2 bytes as a new element to my dictionary of possible values, and that means I can have 257 different values for a byte, so to speak, that I can shrink the length of my sequence, and I can repeat over and do that again. And so essentially this work suggested well, we could apply this kind of compression algorithm and use it as a way of coming up with pieces of words that were useful, doing it not strictly with bytes despite the name, but instead with characters and character engrams. And so the most common way to do this is with characters and character engrams, and if you're up with modern times, that means there's Unicode, and you can represent all of these lovely letters like Canadian Inuktitut syllabics and stuff like that. But there's actually a problem with Unicode, which is, there are actually a lot of Unicode characters. I forget the number theoretically. I think there's sort of 200,000 possible Unicode characters. But anyway, if you want to handle a bunch of languages, which include East Asian languages, maybe you need something like 20,000 characters, and that's sort of a lot. So there are actually some people who've literally gone back to bytes and said, 200,000, that's a really big vocabulary. I don't want to deal with anything. Sorry, 20,000 is a really big vocabulary. I don't even want to deal with anything that large. So why don't I actually just do these kind of algorithms over bytes? And so that means that in UTF-8 encoding, Chinese characters take 3 bytes each. And so you actually have to, and you only get whole characters if you've actually merged together several bytes that are common sequences. Okay, so more concretely, how does this work? So we're sort of doing this bottom-up clustering of short sequences. So we start with a unigram vocabulary, which is all of the Unicode characters in some data. We then sort of ask, what's the most frequent n-gram here? Initially, it'll be a bigram pair, and we add that to our vocabulary. So if we start off, we can take our text that's, I'll come back to this in a minute. Let's assume we have a text that has been divided into words. So we do have word tokens. And so we can represent it as a dictionary and say, here are some words with their frequency. And so now we look for a common letter sequence and we say, oh, ES, that occurs 9 times in this data because we have the counts for the words on the left side. So we start with our vocabulary being all the individual letters. We find a commonest letter sequence like ES, and so we say, let's clump that together and make that a new thing in our vocabulary. So now we've got an extra thing in our vocabulary. And now what's the commonest n-gram sequence that clumps something? Well, actually all of these ESs are followed by T, so we also have EST with frequency 9, and so we can add that to our vocabulary. And then we ask again, well, what's another common letter sequence? Let's see, there are 7 cases of I guess there are 7 cases of either LO or OW, so we can lump those, and then we can lump again and make an LOW. So if we sort of run this, we start to build these clumps of common letter sequences, and so common bits like EST, but also just common words, something like that in English will very quickly be clumped together and be a unit of our vocabulary. And so we do that for a while. So normally what we do is we decide a vocabulary size that we want to work with. We say, okay, I want to work with a vocabulary size of 8,000 words. That'll mean my model will be fast. And we just sort of keep doing this until we have 8,000 things in our vocabulary. And that means our vocabulary will have in it all single letters, because we started with them, and it'll have common subsequences of words like the ES and the EST that are now in our vocabulary, but it'll also have whole words whenever they're common. So words like, that and to and with and so on will become parts of our vocabulary. And so then when we have a piece of text, we can do a deterministic longest piece segmentation of words, and we will say that is our set of word pieces. And so for an input piece of text, we turn into word pieces, and then we just run it through our MT system as if we were using words, but really it's pieces of words. And then on the output side, we just concatenate them back together as needed. Okay, so we get this sort of automatic word-based system. And that's proved to be a very successful system. So this idea of using byte pair encoding sort of really emerged in 2015, and in the 2016 workshop on machine translation, which has been the main sort of annual competition for MT systems, that the several top systems were built using byte pair encoding. If you look at last year's competition, there's a bit more variety, but really a number of the top systems are still using byte pair encoding. That's just been a good way to do things. So for Google's neural machine translation, they effectively use a variant of byte-pair encoding. So they don't use exactly the same algorithm. They use a slightly different algorithm where they're using a language model, and they're saying rather than just using pure counts, they're saying what clumping together would maximally reduce the perplexity of my language model and clump those things and repeat over. And so they've done two versions of this model. So the first version, the word piece model, kind of like byte-pair encoding, assume that you have an initial tokenization to words, and then you're just sort of having pieces of words using this algorithm. But then they did a second version, the sentence piece model, which you can find at this GitHub site, which said, well, it's problematic if we need to tokenize into words first, because then we need to have a tokenizer for every language, and that's a lot of work. So maybe instead of that, we could just sort of go from a character sequence, retain white spaces, and regard that as something that's part of the clumping process. And so that you just build your word pieces, which commonly will have spaces on one side or the other of them, because often things inside a word are the more common clumps, and you build those up. And that's proven to be quite successful. In particular, one place where some of you might see this is, we've yet to get to describing it in the class really, but there's been this recent work, which we actually talk about next week in class, of building these transformer models. In particular, Google has released this BERT model, which gives you very good word representations. And if you download BERT and try and use it, what you will find out is it doesn't operate over words, it operates over word pieces. And so it has a large vocabulary. It's not a vocabulary of like 8,000 words. I forget the number, but the models have a large vocabulary, but they're still not a huge vocabulary, and it's using word pieces. So lots of words are in the vocabulary. So if you look at the English model, it not only has words like at in it, but it even has words like Fairfax and 1910s, which aren't that common. But it's nevertheless, to cover all words, it's again using this word piece idea. So if I want a representation for the word Hypatia, that's not in the vocabulary, and so I'm making it up of pieces. There's an H representation, and then in the BERT version, which is different to the Google NMT version, the non-initial word pieces are represented with two hashes at the start, so I can put that together with H, hash, YP, etc. And this would be my representation of Hypatia. So effectively I have word vectors for 4 word pieces, and then I have to work out what to do with them. The simplest and quite common way is I just average the 4 of them, but there are obviously other things you could do. You could convnet and max pool, or you could run a little LSTM or something to put together a representation. Okay. Yeah, so those were the models that sort of worked with pieces of words to give you infinite vocabulary and ran them through a normal system. The other possibility is to say, well, we want to work with characters so we can deal with an infinite vocabulary, but we're going to sort of incorporate those into a bigger system. And a whole bunch of work has done this. In some sense, it's a fairly obvious thing to do. So this work in 2014 was one of the early ones. So they said, well, we could start with characters. We can do a convolution over the characters to generate word embeddings. And then we can use those word embeddings for something in a higher level model. This was actually sort of a fixed window model for doing part of speech tagging. That makes sense. Instead of a convolution, you could use LSDM. So this was work from a year later, and they said, well, we're also going to build up word representations from characters, and the way we're going to do it is we're going to run character level by LSTMs, concatenate the two final states, and we're going to call that our word representation, and then we're going to put that word representation into a language model, which is then a higher level LSTM that works along a sequence of words. And I thought I'd just, oh, yeah.
Were they training like character embeddings?
Yes. Oh, yeah. That's very important to realize. Yes. So yeah. So if you're learning, I mean, this is the hidden layer. I guess I'm not actually showing the input layer, but for the input layer, you're learning a vector for each character. So effectively, you're doing the same kind of thing we saw before, that you're starting with random representations for each character. You've got this embedded inside a word sequence, LSTM. Your goal is to minimize the perplexity of the higher level LSTM as a language model. And so it filters back its gradient, so it's wanting to come up with character vectors such that it produces good word vectors, which produces low perplexities. Good question. So here's a slightly more complex version of trying to do this that's a bit more recent, where again the idea is, can we build a good language model by starting out from characters and wanting to exploit sort of related subwords and rare words. And so they built sort of this kind of more stacked complex model that we'll go through the stages of, wherefore we start with a word represented as characters. We have character embeddings, which we build into a convolutional network, and then we head upwards. So if we take that one piece at a time, so you have a character embedding for each character. You'll then have a convolutional layer, which then sort of has various filters that work over those character sequence of 2, 3, and 4 grams of characters. So you're getting representations of parts of words. Then from those convolutional networks, you're then doing max pooling over time, which is effectively sort of like choosing which of these n-grams best represents the meaning of a word. Then what they do after that is, so at that point, they've got an output representation for character n-grams. And so then they feed that into a highway network like we talked about a bit last time. And then the output of that then at the word level goes into an LSTM network, and this LSTM network is now a word level LSTM network, and you're trying to sort of minimize perplexity like for the neural language models we saw earlier. So what could they show with this? Well, the first thing they could show with it is that it actually, again, just works well as a language model, despite that skepticism that I hadn't told you of about. The fact of the matter is you can build these kind of character level models and train them, and they work to a first approximation as well as word level language models. But one of the observations that they make is that you can be getting as good results but with much smaller models. So up the top here are their character level LSTM models and word ones, but the models they built. And here are a whole bunch of models over this data set. And so as time went by, perplexities have been going down, gone to 78.4. And their point was, well, we can build pretty much as good a character model with 78.9 perplexity, but our model is actually much smaller. This model here has 52 million parameters, whereas our model that works on a character level has only 19 million parameters, so it's about 40% of the size, and that seems kind of interesting. But perhaps what's more interesting is to sort of peek inside it and see what happens with the representation of words when built out of characters. And this part is sort of actually a bit cool. So what this is showing is for words that are up the top, while here's you, Richard, trading, it's asking what other words are most similar to it according to the word representations that's computed. And the top part is the output of a word level LSTM model, and that's sort of okay. Richard comes out as similar to Jonathan, Robert, Neil, and Nancy, etc. While, although, letting, though, minute, mainly okay. But it's sort of interesting what happens with their character level models. And so in particular, what's kind of interesting is, like, first of all, you remember they sort of had the character embeddings that went through the convolutional layer and the max pooling. And if at that point you ask what things are most similar, that basically it's still remembering things about characters. So the most similar words to while, chili, whole, meanwhile, and white. So at least for the sort of first ones, they all end in LE. And you see that pattern elsewhere, right? Close to Richard, hard, rich, richer, Richter. That hard ends in ARD, rich, that you're sort of just getting this character sequence similarity. It's not really doing meaning at all. But interestingly, when they then putting it through the highway layers, that the highway layers are successfully learning how to transform those character sequence representations into something that does capture meaning. So if you then say at the output of the highway layers what words are most similar, then it seems to be working pretty well. While is similar to meanwhile, Richard is similar to Edward, Gerard, Edward, Carl, that it's sort of now working much more like a word level model in capturing semantic similarity. So that seems kind of cool. So then they say, well, what about if we ask about words that aren't in the vocabulary of the model? Well, if they're not in the vocabulary of the model, the word level model can't do anything, and so that's why you get those dashes there. And what they're wanting to show is that the character level model still works pretty well. So if you give it look with 7 O's in the middle of it, that it's correctly deciding that look, looks, looked, looking are actually the most similar words to that, which is actually working very nicely. And some of the other examples are similar. Computer aided is seen as most similar to computer guided, computer driven, computerized computer. You're getting pretty similar, sensible results. And then the little picture on the right is sort of showing one of these 2D visualizations of the units that have been learned. And so the red things are word character prefixes, the blue things are character suffixes, the orange things are hyphenated things, like in the middle of computer guided, and gray is everything else. And so there's some sort of sense in which it's picking out different important parts of words. Okay. And that's also, I guess, just another good example of how you can sort of compose together different kinds of building blocks to make more powerful models, which you might also want to think about for your final projects. Okay. So here's back to one other example from a neural machine translation system of doing this hybrid architecture that has word level and character level. I showed you earlier a purely character level model. I mean, we'd built that out of interest to see how well it did, but we were sort of really wanting to build a hybrid model because that seemed like it'd be much more practical to build something that translated relatively quickly and well. So the idea was we'd mainly build a word level neural machine translation system, but we'd be able to work with character level stuff when we had rare or unseen words. And that turned out to work pretty successfully at improving performance. So the idea of that model is this, that we were going to run a pretty standard sequence to sequence with attention LSTM neural machine translation system. In my it's actually a 4-level deep system, but in my picture I showed less than 4 levels stacked to make it easier to see things. And we're going to run this with a reasonable vocabulary of 16,000 words. So for common words, we just have word representations that we're feeding into our neural machine translation model. But for words that aren't in the vocabulary, we're going to work out a word representation for them by using a character level LSTM. And conversely, when we start to generate words on the other side, we have a softmax with a vocabulary of 16,000. It could just generate words like sha, but one of those words is the unk symbol, and if it generates the unk symbol, we then run a we take this hidden representation and feed it in as the initial input into a character level LSTM, and then we have the character level LSTM generate a character sequence until it generates a stop symbol, and we use that to generate words. Okay, so we end up sort of with this sort of hybrid composed stack of 8 LSDM layers. Yeah?
Model, and you always get some probability for the unk symbol. So if you wanted to get the proper gradient, you would always have to run it for every word, right? Or do you cut it off and say you only run, like during training, you only run the character level LSTM when the unk symbol receives the highest likelihood? But is that...
So at training time, there's a determinate piece of text, right? You know the source and you know the target. And so at training time, we've already decided our vocabulary, right? That we've just decided what are the 15,999 most common words. Those and unk are our vocabulary. So for both the input and the output side, we know which words aren't in our vocabulary. And so if it's not in our vocabulary, we're running this one. If what was the output is not in our vocabulary, we're running that one. And otherwise, we're just not running it at all. Yeah. And so, and the bit that I didn't explain, but is actually important and perhaps related, like when we're calculating a loss that we can back propagate, that sort of up here there are sort of 2 losses. There's a loss at the word level that you'd like to in this position give probability 1 to generating unk, but really this model will softmax will say unk is probability 0.2 or whatever. So there's a loss there. And then secondarily, there's a particular sequence of characters you want to generate, and you've also got a loss because of the probabilities you put over the characters. So then, I think Abby sort of briefly mentioned this. Commonly, the decoders do some kind of beam search to consider different possibilities before deciding the highest probability one over a sequence of words. And so this was doing a slightly more complex version of that. So there's a word level beam search when running it, and then also doing a character level beam search to consider different possibilities. And so if you want to integrate the 2 of those together. But essentially, this worked pretty well. This was the winning system in WMT 2015, which used 30 times as much data and ensembled together 3 other systems compared to the data that was provided for the task. This was the system I showed before that got 18.3. And if you remember, our purely character level system got 18.5. But by building this hybrid system, that we were able to build a much better system that was about 2.5 blue points better than either this word level or the character level system. So that was kind of nice, and in particular, that was the state of the art at the time. Now, of course, if you were paying very close attention, that's now nowhere near the state of the art, because when I showed you that slide way earlier of the Google system, you will have notice that they have much higher numbers in the 20s, but that's what happens as the years go by. Okay, but here's an example that shows these different systems working and some of the mistakes they make. Here's a cherry-picked example where our system, the hybrid system, works perfectly, because what else would you expect to see? And so, you can see some of the defects of things that can go wrong. So in this case, the character level system didn't work here because it just sort of, starting with the Steph, it sort of seemed to free associate a completely made up name that doesn't really have anything to do with the source. So that one isn't very good. The word level system went bung here. So you remember when it generates an unk, the word level system would have, when it generates, it's using attention. So when it wants to generate, it has attention back to words in the source. And when it generates unk, it has two strategies. It can either do unigram translation of the word that it's maximally putting attention on, or it could copy the word that it's maximally putting attention on. So in this case, it chose to translate the word it was maximally putting attention on, but the word it was maximally putting attention on was after rather than diagnosis, and so you just get this po coming out of after, and we've completely lost the word. And in this example, our hybrid system just ends up working beautifully and gives you exactly the right translation. Yay. Of course, it's not always that good in the real world. So here's a different example. So this is the example I showed before with the 11-year-old daughter. And in this example, the hybrid model has the same strength of the character model. It correctly generates 11 years old at a character level in its translation. But this time, for whatever reason, it's the hybrid model that goes bung in generating the names, and it translates Shani Bart as Graham Bart, whereas the character level model gets it right. Actually, I think this is one of the weaknesses of this hybrid model compared to the character level model, that because of the character level generator is kind of this sort of second level. For the purely character level model, it's able to use the character sequence as conditioning context very effectively, whereas our hybrid model, although we feed the hidden representation of the word level model in as the starting hidden representation of the character level model, it doesn't have any representation further back than that of what's in the word level model. And so it tends to not always do as good a job at capturing the context that allows it to do translation of things like names. Okay. Very almost finished, but there was just sort of one thing I wanted to mention before the end, which is almost a practical thing. So we started off with word embeddings, but now we've been talking a lot of character level models. So surely just for word embeddings, you should be able to do useful things with them with characters or pieces of words. And that's something that people started to play with. So in this Cow and Ray paper, they said, well, let's train a word-to-vec model using exactly the same loss as word-to-vec users, but let's, rather than having word representations, let's start with character sequences and run a bidirectional LSDM to work out word representations, and we'll then sort of be effectively training this more complex model where we're learning character embeddings and LSDM parameters, and that will give us our word representations. And that's an idea that people have continued to play with. And so in particular, I just wanted to mention these fast text embeddings. So a couple of years ago, people now at Facebook, the same Tomasz Mikolov who did the original Word2Vec, brought out a new set of embeddings, the fast text embeddings. And their goal was to sort of have a next generation Word2Vec, which is sort of an efficient, fast word vector learning library but was better for rare words and languages with lots of morphology. And the way they did it was that they sort of essentially took the word-to-vec skipgram model, but they augmented it to put in character n-grams. So more precisely, this is what they did. So when you had a word, my example word is where, for some n-gram size, you represent it as a set of n-grams. So this is kind of just about like those Wickle phones I mentioned right at the beginning, where you have a kind of a boundary symbol so you know the beginning of the word. So if the length is 3, you have beginning of word WH, WHE, HER, ERE, RE, end of word as pieces of representation. And then you have an additional one for just the whole word. So you do still have whole word representations in this model. So where is represented by 6 things. And so then you're going to use all 6 of those things in your computation. So if you sort of remember the guts of word2vec, that what you were doing was you were doing these vector dot products between your context representation and your center word representation. So they're going to do exactly the same thing, but for the center word, they're going to use all 6 of these vectors, the vectors corresponding to all 6 of these representations, and they're going to sum them. And so you're just doing this simple summing operation, and that's sort of then giving you your representation of similarity. Very precisely, they don't quite do that because there's a hashing trick, but I'll leave that out. But what they're able to show is that that model actually works pretty successfully. So these are word similarity scores, skipgram, their old Siebel, and then this is the sort of new model that uses these kind of n-grams. And in this, at least for one of the English data sets, it doesn't get any better. But what they especially notice is for languages that have more morphology, that you're sort of getting some fairly clear gains, 70-69 onto 75, 59-60 onto 66 in the right column, so that these word piece models do give them a better model of words. And just practically, fast text library now has sort of word embeddings for about 60 or 70 different languages, so it's sort of a good source of word embeddings for multilingual applications. Okay, I think I am done. So thanks a lot, and see you again next week.